All right, so we have the iodine clock reaction demonstration here today. Just to remind you, here is the overall equation. We're mixing potassium iodate with sodium metabisulfite. We get all sorts of different products. The important one here that we're going to get is iodine, I2. Okay? And remember, the reason why that's important is because once it's formed, once the reaction is done, it's going to combine with the starch that's going to be in each reaction mixture, and it's going to turn blue. Okay, and that way we know the reaction is over. All right, refer to your handout here with this table. It's table 2. So we'll use this to track each of the different reactions. We have 6 different reaction mixtures. Recall, we talked about this the other day. The potassium iodate, the KiO3, that concentration changes, at least in those first 3, whereas the sodium metabisulfite concentration is constant. And again, the reason we need that is that to be constant. Once that is consumed, then the reaction's over and we get the blue color. So that has to be constant the whole time. All right, so I have 6 different mixtures set up here. They're labeled 1A, 1B, 2A, etc. All we'll do for each one is I'll pour the contents of the B beaker into the A beaker, okay? Our timer, which is Mr. Manis, is going to start as soon as the solution starts to mix. So I'm going to pick the beaker up, I'm going to pour it. As soon as you see that it first enter the solution, start it, and then stop it when you see the blue color, okay? All right, so we will try this first one out here, but before we do that, we need to take its temperature. So we'll see the temperature here. All right, give me just a moment. So it should be right at room temperature. It should be about 20 degrees Celsius. Looks like it's a little above that, actually. We're getting there, slowing down. We're at 22 degrees Celsius. So for the temperature here, for number 1, and actually for numbers 1, 2, 3, and 6, you can go ahead and write 22 degrees Celsius in for each of those. Okay, because those are all at the same temperature. 4 and 5, we have varied. Okay, so we are ready now. Adam, are you ready, sir?
Yes.
All right, so we're going to pour 1B into 1A. And I'll wait till we got the camera ready to go there. We all set, sir? All right.
Oh, you messed it up. Oh. Wow.
The time, Mr. Manis.
8.08 seconds.
I'm just going to round to the nearest tenth. I'm going to say 8.1 seconds. There was no catalyst in that mixture, so I'm just going to put it in there for catalyst. All right, so this first reaction is our control reaction. Every other one we do, we are going to compare to this one. So if you look at the questions on down below there for number below effective concentration on the rate, I'd like you to make a prediction as far as how the rate is going to compare to number 1. Okay, so go and take a couple moments, write down your prediction there, look at how reaction 2 is going to be different. Okay, look at what's different about number 2 compared to number 1. Okay, and write down a prediction.
I got it.
Grab what?
My sheet.
Where is it?
It's like my.
Yeah, need it. Would anyone like to share their prediction with us? 10.
5.1 seconds.
I wasn't looking for an actual time.
Oh.
Why do you say it's going to be less time, sir?
Because I'm assuming you're going to have a catalyst and that'll make it react faster.
There is no catalyst in this one.
Does he have more? I don't know.
Anyone else? Or?
I think the rate will stay the same because if you look at the 2 numbers, they're the same. So I feel like
The same as number 1?
Well, no, like the,
I get that the concentration is the same as each other,
yeah,
but compare it to number 1 though. Trey, what do you say?
I think it's gonna be slower because there's more KiO3. So I don't know.
Any other predictions? Elizabeth?
I think it's gonna be faster because there's more gas.
Quite the competition here. All right. Shall we find out who's right?
There's only enough room in this room.
All right.
Make sure it's clear.
Here we go. 2B into 2A.
Someone has to know that it's bad.
Ready, Adam?
Yeah.
Okay.
Low.
Yeah.
4.96 seconds.
4.9, so 5.0 if you round it to 1 decimal place. So no catalyst there. In fact, there won't be a catalyst until we get to step 6. So you guys can go and put an in for the catalyst there. Step 6 is acid catalyzed. All right. So now make a prediction for the next one. Okay, again, look at the reaction contents there. Again, compare it to reaction number 1. What do you think is going to happen? Well, is it going to be faster or slower? Elizabeth, what do you think?
Slower,
Because?
there's less of the gas.
So she won the first battle. You're going to challenge her on this
No,
one too,
because I
right?
don't know. You know, just for what's and what's. Yeah, sure.
All right. Let's try it out here. So 3B into 3A. Ready, Adam?
Yep.
Okay.
It's a lot slower.
Bro, what?
19.11.
19.1 seconds.
Yeah, that's pretty close to it.
How much was it?
Felt like forever.
19.
All right. For, we're actually going to, let me turn this guy back up. We're actually going to do number 5 before we do number 4 because I need to heat this up just a little more. So for number 5, I have had beaker 5A in a ice water bath here. Okay, so it's colder. So we'll get the temperature for number 5. And the number 4 cooled down a little too much for what I wanted. So let's see what number 5 is at here. I guess it's about 10. It's kind of what I'm shooting for. All right, so for reaction 5, that is right about 10 degrees Celsius. 10 degrees Celsius. So find the question there. Oh, that's the wrong one. 10 degrees Celsius temperature up here. Not that. Find the question there. We're talking about the effect of temperature on reaction rate. And for the cold one, this would be reaction 5. Okay, this is number 5, and we're skipping 4 for now. I want to heat that back up just a bit. So it's a little cold in for what I wanted. Okay, make a prediction. Is this going to be faster or slower than beaker 1, reaction 1? And notice, for reaction 5, we're back to the same concentrations we started with, aren't we? Okay, we have the same concentrations in 5 as we had in 1. The only thing that's different now is the temperature. All right, someone like to make their prediction known? Chance.
I say it's gonna be slower.
Do we agree it will be slower?
Yes.
Except for little, she thinks it's gonna be faster.
Elizabeth thinks it's going to be faster?
No, it's gonna be slower.
Good. Elizabeth thinks it's going to be slower. All right, let's try it out here. Now, I'm a little concerned about this one because I shorted my starch solution, and so I had to dilute it a little much between 5 and 6. So I hope it works. We'll see. Our time, Mr. Manis?
13.27.
All right, so did that match the prediction of being slower than reaction 1? It did. Okay. So this is warm enough now. All right. So now we're back to number 4, and this is at 41 degrees Celsius. 41 degrees Celsius is where we are for number 4. All right. Anyone like to make their prediction known for that? Trey.
Don't be fast.
Fast compared to
Second. Number one, yes.
compared to number 1. Okay. Let's find out.
I wanna make sure
All right. Thermometer out here. All right. Ready, Adam?
Yep.
Okay. Here we go. 4B into 4A.
– 5.7 seconds.
So it is faster. Okay. And the last reaction here, if you would flip back in your handout to table 1, I'm not going to move it up here. You guys can do it yourself. What is in beaker number 6 that is not in any of the others?
Catalyst.
And what is the identity of that catalyst, sir?
H2SO4.
Shannon, or should we try?
H2SO4.
Yeah, which is sulfuric acid. This is an acid catalyzed reaction. So that is present here. That's not in any of the others. All right. So last one. You ready, Mr. Manis?
Yep.
Okay. Here we go.
Whoa, wow.
Wow.
And the
Wow.
result is
2.5 seconds.
2.5 seconds. And that, ladies and gentlemen, concludes the demonstration on iodine clock kinetics.